Hello everyone, I am Shaikha Mokhlis and I will be the speaker for this review paper, which was conducted by me and my colleagues Reem Al-Shawi, Al-Anud Al-Hamoud and Shad Al-Hazzani. I will be presenting our comprehensive review on crack detection using conventional neural networks. This research is critical for ensuring the safety and integrity of structures such as buildings, bridges, and roadways. Throughout this presentation, I will provide an in-depth analysis of CNN architectures used for crack detection, discussing their comparative performance, and highlight future research directions. Here's an overview of what we'll be covering in our presentation. We'll start with the background, discussing traditional crack detection methods and their limitations. Then we'll outline the key research questions that guided our review. We'll explain our approach and criteria we use to select relevant studies. We'll present our findings focusing on effective image processing techniques and the most commonly used CNN architectures. We'll interpret our results and discuss their implications for the field of crack detection. We'll address the limitations of current research and identify areas for further investigation. And finally, we'll summarize our key findings and suggest future research directions. Traditionally, crack detection has relied heavily on human visual inspections. Inspectors manually examine structures for visible cracks and use measurement tools to assess their severity. While this method is still widely used, it has significant limitations. This image illustrates the traditional inspection process, showing an inspector carefully examining a structure of cracks. As you have seen in the previous image, these traditional methods are subjective and inconsistent as they depend on the inspector's experience and judgment. They are also time-consuming and labor-intensive, making them impractical for large-scale inspections. Moreover, fine cracks or cracks in hard-to-reach areas can be easily missed, posing a risk to structural integrity. Given these limitations, there is a clear need for automated crack detection systems. Automated systems can provide a more accurate, efficient, and consistent analysis by leveraging advantages in image processing and deep learning. Early detection of cracks is critical for maintaining the safety and integrity of structures, and automation can significantly enhance this process. To guide our review, we focused on 4 research questions that address different aspects of crack detection using conventional neural networks. These questions are critical for understanding the current state of research and identifying the most effective methods and technologies. Research question 1. What image processing techniques are most effective for enhancing the visibility and depth perception of cracks in images? We examined various image processing techniques to determine which ones best enhance the visibility and depth perception of cracks. This is important because clear images are essential for accurate crack detection and analysis. Research question 2. How does the architecture of neural networks impact detection and detection accuracy? We explored how different neural network architectures affect the accuracy of crack detection. The design and depth of the network can significantly influence its performance, so understanding this relationship is key to developing effective detection systems. Research question 3. How can CNNs be applied to detect and quantify cracks? This question investigates the particular application of CNNs in detecting and measuring cracks. We looked into various methods and techniques that leverage CNN for this purpose, aiming to identify the most successful approaches. Research question number 4. What architectures are utilized in CNN for crack detection? Finally, we compared different CNN architectures used in crack detection to determine which ones are most commonly used, and this helped us understand the current preferences in the field and the reasons behind them. To ensure a comprehensive review, we conducted a thorough search using Google Scholar and Science Direct. We used specific search terms such as analyzing home cracks from images and a combination of keywords related to properties, damage detection, and AI. Our focus was on publications from 2019 to 2024, providing a recent and relevant overview of the field. We established clear criteria for selecting the most relevant papers. Our primary focus was on studies related to detecting and quantifying cracks, as well as evaluating detection accuracy. We identified 20 papers that met our criteria. To expand and refine our research, we employed specialized tools like Litmap, Humita, PopAI, and ChatPDF, which helped us ensure that our research was as comprehensive and as up to date as possible. The image you see on the right shows a research map created by Litmaps. Litmaps is a tool that helps researchers discover and visualize connections between papers by creating citation maps. It visually represents the network of related research, highlighting how papers are interconnected through citations. This allowed us to easily identify key works and relevant literature, ensuring our review is as thorough as it can be, given that it's only 20 research papers. From the selected papers, we extracted detailed information on various CNN architectures, image processing techniques, and their application domains. We performed a comparative analysis of these architectures, evaluating their performance in crack detection tasks. We also assessed the frequency of utilization of different CNN models and examined their performance metrics to identify trends and insights in the field. In this section, I'll present the key findings from our review. Organized by our 4 research questions, this will provide a comprehensive understanding of the current state of crack detection using CNNs. For our first research question, we found that several image processing techniques significantly enhanced the visibility and depth perception of cracks in images. This image illustrates the techniques we used. As you can see, contrast enhancement, as shown in the image, this technique improves visibility by bringing out subtle details, making even minor cracks visible. Noise reduction. Here you can see how noise reduction techniques enhance detection accuracy by eliminating irrelevant background information. Edge detection. This part of the image highlights the boundaries of the cracks, making them stand out clearly. As for threshold segmentation, this technique effectively separates crack regions from non-crack regions as shown in the clear demarcations in the image. Boundary tracking. Finally, boundary tracking is used for quantification, helping to measure the extent and dimensions of the crack accurately. For our second research question regarding the impact of neural network architectures on accuracy, our review shows that the deeper architectures tend to perform better in crack detection fields. However, it is important to balance the depth to avoid overfitting. Now, for research question 3, when examining how CNNs can be applied to detect and quantify cracks, we found that patch-based categorization and transfer learning from pre-existing architectures are effective approaches. Customized loss functions tailored to crack detection also improve accuracy. Additionally, innovative frameworks like digital image correlation, displacement fields, and self-organizing maps further enhance detection and quantification accuracy. For our final research question, we identified that ResNet, GoogleNet, and VGG16 are the most used architectures for crack detection due to their high, robust performance and computational efficiency. AlexNet, YOLO version 4, and YOLO version 3 are less frequently used, but they still play a role in specific applications. The bar chart you see on the right represents the usage frequency of these architectures in our research. As I have stated, ResNet, GoogleNet, and VGG16 have the highest frequency of use, demonstrating their popularity and effectiveness in crack detection tasks. In contrast, architectures like AlexNet, YOLO version 4, and YOLO version 3 have a lower frequency of use. In this discussion, I'll interpret our key findings, highlight their implications for the field, address limitations, and suggest directions for future research. This will help contextualize our research and their importance in advancing crack detection technologies using CNNs. Our review provides several key insights. Research question 1. Effective image processing techniques such as contrast enhancement and edge detection significantly improve the visibility and analysis of cracks. This underscores the importance of pre-processing steps in crack detection workflow. Research question 2. The architecture of neural network greatly impacts detection accuracy. Deeper networks like ResNet and VGG16 constantly outperform shallower ones, highlighting the need for sophisticated models in achieving high accuracy. Research question number 3. CNNs can be effectively applied to detect and quantify cracks using techniques like patch-based categorization and transfer learning. Customized loss functions and novel framework enhance the performance further. Research question 4. The prevalent use of architectures like ResNet, GoogleNet, and VGG16 indicates their robustness and effectiveness in crack detection tasks. The choice of architecture is influenced by the balance between accuracy and computational resources. These findings have several practical implications. Engineers and researchers can leverage our insights to select appropriate image processing techniques and CNN architectures for their projects. This can lead to more accurate and efficient crack detection systems, which are critical for maintaining the safety and integrity of structures like buildings, bridges, and roadways. Future research should address these limitations by exploring the resilience of CNN-based crack detection systems under diverse conditions. There is also a need for scalable and real-time detection methods that can be applied in different scenarios. Further advancements in neural network architectures and image processing techniques will likely continue to enhance detection accuracy and efficiency. In this section, I'll discuss the limitation of the studies we reviewed, the limitation of our own review, and identify gaps in the current research. This will provide a balanced perspective on our findings and highlight areas that need further investigation. Firstly, the reviewed studies have several limitations. Lack of diversity in datasets. Many studies use limited datasets that may not represent the wide variety of crack types and conditions encountered in real-world scenarios. This limits the generalizability of their findings. Limited real-world applicability. Some studies focused on controlled environments, which may not accurately reflect the challenges of detecting cracks in real-world settings. Potential bias based in study design. There could be bias in how studies are designed and conducted, such as the selection of specific architectures or techniques, which might influence the results. Our review itself has certain limitations. Scope limited to certain architectures and techniques. We focused on specific sets of CNN architectures and image processing techniques, which means we may have overlooked other potential effective methods. The dependence on the available literature. Our conclusions are based on the literature available to this point. There may be newer studies or unpublished data that could provide additional insights. Possible omission of relevant studies. Despite our efforts to conduct a comprehensive review, there is always the possibility that we missed relevant studies. There are several gaps in the current research that need to be addressed. The need for more robust and diverse datasets. Future research should focus on developing and using more diverse and representative datasets to improve the generalizability of findings. Exploration of real-world application scenarios. Studies should investigate the practical application of crack detection systems in real-world settings to ensure their effectiveness and reliability. Investigation of scalability and generalizability. Research should also explore how well these systems scale to different types of structures and conditions, as well as their ability to generalize across various scenarios. Based on these limitations and gaps, we recommend the following areas for future research: development of comprehensive datasets, creating and sharing large, diverse datasets that cover a wide range of crack types and conditions will help improve the robustness of crack detection systems. Focus on real-world applications. Researchers should test their systems in real-world scenarios to identify and address practical challenges. enhancing scalability and generalizability, investigating methods to make crack detection systems scalable and generalizable across different structures and environments will enhance their utility and effectiveness. In conclusion, I'll summarize our key findings, highlight the significance of our review, and discuss the future directions for research in the field of crack detection using conventional neural networks. Our review provided several key insights. Effective image processing techniques are essential for enhancing crack detection and quantification, demonstrating the need for integrated approaches combining CNNs with advanced image processing. Application of CNNs. CNNs can be effectively applied for crack detection and quantification, with techniques like patch-based categorization and transfer learning enhancing their performance. Prevalent architecture. ResNet, GoogleNet, and VGG16 are the most commonly used architectures chosen for their balance between accuracy and computational efficiency. ResNet is identified as the top performing CNN architecture for crack detection. Looking ahead, future research should focus on developing robust datasets, creating comprehensive datasets that represent wide variety of crack types and conditions to improve the generalizability of detecting systems, real-world applications, testing and refining crack detection systems in real-world scenarios to ensure their practicability and reliability. Scalability and generalizability. Exploring methods to make detection systems scalable and adaptable to different structures and environments. In conclusion, our review highlights the significant advancement in using CNNs for crack detection and potential for further innovation in this field. Continued research and development are essential to enhance accuracy, efficiency, and applicability of these systems. I would like to thank Dr. Lemis El-Hazzak for her supervision on this review paper and her continuous help and support, as well as my colleagues for their contribution to this review. And thank you all for your attention.